Alrighty, this is going on page 88 when we are done. Linear and angular speed, or circular motion. Tell me, what is another word you know related to speed? Velocity. Speed and velocity are very much related. Are they the exact same thing? No. Who can tell me the difference? Layla? She raised her hand. I'm going to let her answer. Go ahead. And speed does not. Very good. Okay, so speed gives you speed, magnitude. Velocity also gives you direction. So sometimes the words are used interchangeably, but they're not really the same thing. It is possible that speed and velocity could be the same thing in given situations, but not always. All right, and we're not just talking about linear and angular speed in general. We are talking specifically circular motion. So it's all going to be within a circle for us, okay, going around in circles, revolutions and whatnot. Which is where the angular speed comes in. But linear speed, I mean, that's something you don't necessarily have to be on a circle for. So here's what this says. This says, arc length can be used to analyze circular motion. All right, so it says, suppose an object moves along a circular path S with radius r. So here's an object. It's moving along a circular path, which is S. That's our arc length. Our radius is r. Okay, so we're moving along this way. This is our radius. And we're using arc length, which we did last week, but it seems like forever ago now, so I'm just going to remind you that arc length was a lowercase s, and that is r times theta when you're in radians. Okay? I think it was literally a week ago. I think we did it on Monday. So s equals r theta. So we're going to be using that. That's why we had to do that first. Okay, so the rate at which the object moves along the path, so if you think about this as a track we're running around, the speed at which you're actually running around the track, how fast you're going in feet per minute or whatever, that is your linear speed, denoted by a lowercase b. So v is equal to s, oh, my pen being weird, s over t. Distance over time. Okay, it's just that the distance in this case is arc length. And so this is arc length over time. What that actually says. It did not look like time. There we go. All right, so then the rate at which the central angle is changing, so the rate at which you are actually going a complete circle around, so the angle is changing along that path is the angular speed. This looks like a lowercase w, but it's not. It's actually a lowercase omega. So it's kind of a bloated lowercase w. Your angular speed looks like this, omega, which still kind of looks like a lowercase w, but it's like somebody blew air into it or something. That is equal to theta over time, and that is the central angle over time. Okay, so let's think about the difference between this linear speed and angular speed in a circular path. So I'm going to show you this. All right, so I have these two circles, okay, and right now they have the same linear speed and they have the same angular speed. So if we think about this little red dot as being a guy that's running around this circle, okay, so we have guy A and guy B, and they are running one complete rotation in the same amount of time. They're also having to run the same speed around that, right? If I change his circle to be bigger, they still have the same angular speed because they're finishing one rotation in the same amount of time, but who's running faster? Guy B, right? And you can see it if you superimpose it, you can see it a little bit more. And the bigger this one gets, and the smaller this one gets, he's having to run faster and faster, right? Same angular speed, because it still takes the same amount of time to go once around the circle, but the linear speed is different because one circle is bigger than the other. There's more to actually run on. Okay, does that make sense? You see the difference between the two? All right. Oops. There we go. All right. So let's talk about the things we need to know to do all of this. theta, our actual angle, right? So theta is some value that relates to 2 pi, right? And so I need to know how many times I go around the circle. If I go around the circle once, my angle is 2 pi. If I go around the circle just a half, my angle is pi. If I go around the circle 2 full rotations, then it's going to be what? 4 pi, because I'd have to multiply it by 2. So your theta is based on your number of revolutions. This is the number of revolutions times 2 pi. And the number of revolutions may not be a whole number. It's going to be for most of what we do because we're talking about RPMs, revolutions per minute. But again, if you only went around half of a revolution, your angle is going to be pi. So when we're talking angular speed, 1 revolution is 2 pi radians. That's how go all the way around the circle. Oh, I cannot write. For linear speed, 1 revolution. So what do we call in general the distance around the circle? The circumference, and the circumference is 2 pi r. Okay. We all good with that? What questions you got? Okay. All right, so it says here, a bicycle tire with a radius of 14 inches rotates at a rate of 125 revolutions per minute. Okay, find the linear speed of the tire in inches per minute. So my linear speed is arc length over time, right? So I'm going to start by finding my arc length. Arc length is r times theta. They gave me the radius, it's 14. I find theta by the number of revolutions times 2 pi. So I have 125 revolutions per minute. So we're going to use a 1 minute time. And so that means I can use 125 revolutions. So that's 125 times 2 pi. Right. Then you can multiply that in your calculator, leaving the pi out so that you can let it do all the math for you there. And you should get 3,500. You cannot forget to put the pi back in. And then what are the units here? Inches. Okay. All right, so that's just the arc length. My linear speed is 3,500 pi inches. And then I know to use 1 minute because that's where I got my revolutions per minute. So over 1 minute. Then I check my units, and I wanted it in inches per minute. Yes? Oh, did I? Did I write it wrong? Oh, okay. So this is 3,500 pi inches per minute. I didn't have to change the units, so basically ended up like that. Okay. And you can't make up things like IPM for inches per minute. It's inches over minutes. Okay. Or written out inches per minute, but really a fraction is kind of better. Okay. We good with all that? Okay. So then it says find the angular speed of tire in radians per minute. So my angular speed, that's omega equals theta over t. So omega, or actually we went theta first. Theta is the number of revolutions, which is 125 times 2 pi. So that gives me 250 pi. Yes? And then omega is equal to theta, which is 250 pi radians for every 1 minute. So that gives me 250 pi radians per minute. And that is not RPM. RPM is revolutions per minute. And I know you might think it's silly that I'm making you write it as a fraction and then we write it like that, but there's a reason. There's always a method to my madness. What questions do we have? Anything? Okay, so now we're about to venture into the land of things you have to know to be a functional human being, okay? Some of that has to do with conversions, some of that has to do with how things are written, some of that has to do with, knowing how many suits are in a deck of cards, things like that, that you may not think really apply to a whole lot, but it could apply in questions like this, and you got to get through stuff you may not think you needed to know. All right, so this says a 16-inch diameter tire. So this is very important, because on the notes it literally says 16-inch diameter. If it just said a 16-inch wheel, that is the diameter. If you don't know anything about wheels and cars and whatever, you need to know a 52-inch wheel, that is the diameter of the wheel, that is not the radius. Okay, so it may not actually say diameter radius, something you got to know. So I got a 16-inch diameter tire. That means my radius is 8 inches. It's making 500 revolutions per minute. I want to find the linear speed in miles per hour. All right, so my linear speed, arc length over time. So I'm going to start with arc length. Arc length is r times theta. My radius is 8. Theta is the number of revolutions. That's 500 times 2 pi. So 2 times 500 is 1,000, so that gives me 8,000 pi. And that would be inches. Everybody agree with that? So now my linear speed, it's arc length, 8,000 pi inches, and then it's over time. So since I use this 500 revolutions per minute, that means that happens in every 1 minute. And then we have to convert, okay? I have inches per minute. I need this in miles per hour. So you can start with either the numerator or the denominator. I always start with the numerator. It's not because you have to. It's just because that's the way I'm going to do it. And then you need to be able to convert. I need to convert inches into miles. You don't have to do that in one step. Okay? Little steps along the way is probably better for most people because it's probably more what you really know. I know how many inches are in a foot. So if inches is in the numerator, I'm going to put it in the denominator so it cancels out. And I'm going to go from inches to feet. And if I write that in there first, then it's really hard to get this messed up because 1 foot has 12 inches. I still don't need it in feet. I need it in miles. Here comes that life skill that slaps you in the face for most of you. You have to know how many feet are in a mile. How many feet are in a mile? 5,280. That is something you absolutely are expected to know to be able to convert on things without a conversion chart. That's just a life skill. Okay? And so I've canceled out the inches, I've canceled out the feet, that leaves me with miles. So I wanted miles per hour, I got miles. So I always circle it when I'm like, okay, I'm done with that part. So now I got to change my minutes. So minutes is down here, I need it in the numerator so that they cancel out. And I can go from minutes to hours. There are 60 minutes in 1 hour. I've got my miles per hour right there. Okay? If you actually write it down as fractions, you will never get it backwards. Oh, I just have to multiply this. Oh, I just have to divide, because sometimes you get them backwards and it's a 50-50 shot. So you should have done dimensional analysis like crazy in chemistry. But now when you go put this in the calculator, you don't have to put it in as 4 different fractions. When you multiply fractions, you just multiply straight across. You can look at this as one big fraction. So you can hit your fraction button and just do, you can leave all the ones out, because just multiply them by 1. So in the numerator, you're going to have 8,000 times 60. In the denominator, you have 12 times 5,280. And then it should give you your linear speed of, what does the calculator give you? We're leaving pi out, so everything should be exact. Okay, we're leaving pi out, so everything should be exact. What does the calculator tell you? It can't tell you 7.57. 250 over 33. So it's 250 pi over 33. And then your units are miles per hour. Okay. What questions do you have? We good? Okay. All right, so now we have a circular saw blade with a diameter of 9 inches. So if the diameter is 9 inches, then my radius is 9/2 inches. It rotates at 2,800 revolutions per minute. Find the angular speed in radians per second. So your angular speed is theta/t. Okay? And we could go find theta separately and then put it in there, but really it's fine to kind of do it all at once here. Theta I find by doing the number of revolutions, which is 2,800 times 2 pi. Right? So that would be radians up here. The time would be 1 what? Minute. Okay? You have to use what was given to you. We were given 2,800 revolutions per minute, so our original is in minutes. I want this to be in radians per second. So radians are good, but I need seconds. So I put minutes up here so that they cancel out. 1 minute is 60 seconds, bless you. And then again, you can put it all in one fraction. And you should get 280 pi over 3 radians per second. What questions you got? Everybody good? Okay. All right, so then a windmill has blades that are 14 feet long. So is that going to be the radius or the diameter? A windmill. Here's my windmill, right? Where are my blades? With the radius or the diameter? The radius, okay? The windmill is rotating at 5 revolutions per second. Find the linear speed of the tips of the blades in miles per hour. So my linear speed is s/t. I'll find arc length first. S equals r times theta. That's 14 times the number of revolutions, which is 5, times 2 pi. 2 times 5 is 10, so that's 140 pi feet. Then I have arc length, which is 140 pi feet over time, and that was 5 revolutions per second, so this is 1 second here. So I'm in feet per second. I want miles per hour. Right? You write out the conversions there. And you could have gone straight from seconds to hours if you know that conversion, that's fine. In the end, you should get what questions do you have? Anything? Dimensional analysis is not new to you, so we're just applying that to a formula, really. It's plug and chug type of thing. Any questions at all? And I know these have all come out like fractions. It is possible that they could divide evenly. I mean, more often than not, it doesn't. But but you could just get like 237 pi miles per hour or whatever. That might be it. Okay, any questions at this point? All right, so there's another formula, which I always debate whether or not to go over this too. So I went and talked to Ms. Melton, I think a couple years in a row now, because I always forget about our conversations, to ask about whether or not, which formula do you use? What do you actually need to know in AP Physics? That sort of thing. So she told me y'all should be familiar with this one. How many of you are in AP Physics? Okay. You should be familiar with this one. It's distance over time or arc length over time if you're doing circles, but y'all really haven't done angular speed at all. So that's why if they're set up separately, should hopefully make sense. This is, not anything new to you. So this next formula you probably haven't seen yet in physics, but eventually you will when y'all come back and do some angular speed. So we're going to go ahead and look at this one. So it says the linear speed v can also be found as follows. So we know that v is equal to s over t. Okay, that's the one we've been using. So s over t can go right here. All right, and then we're going to kind of change things a little bit along the way. S is arc length. What's your formula for arc length? R theta. So instead of S, I'm going to put R theta up here. So R theta over T. Okay. And then I'm going to rewrite this. This is the same thing as R times theta over T. Would you agree with that? Okay. And what is theta over T? Your angular speed. It's your omega, right? So this is the same thing as R times omega. So this is the formula we've been using. V equals R omega is another perfectly fine one. Which one you use depends on what information you have and which one you're more comfortable with. I don't care either way. Pick one and use it. We're going to do this last example using R omega, but they're really the same thing. Okay? But if you haven't talked about angular speed at all, then the second one wouldn't make any sense. All right, so let's look at this. This says, Ryan is riding a bicycle whose wheels are 28 inches in diameter. So again, this flat out says diameter, but even if it didn't, we would have to know that, right? So our radius is 14 inches. If the wheels rotate at 130 RPM, find the linear speed in miles per hour in which he is traveling. So we're going to use V equals R omega. So we're going to find omega first. Omega is equal to theta over T. So we find theta by the number of revolutions, 130 times 2 pi, and that would be radians, and this time would be 1 minute. Right? So this gives me 260 pi radians for every 1 minute. And I'm just going to leave it like this because we're about to use it again. Okay. Everybody okay with that? So now V is equal to R omega. So I'm going to have to do some dimensional analysis. I really want things in a fraction form right now. My radius is just 14 inches. So I'm going to make this 14 inches over 1. Times omega, which is 260 pi radians for every 1 minute. Okay. All right, so I have it in inches per minute. I want it in miles per hour. So let's start with the numerator here. I know I can go from inches to feet, and I know inches are in the denominator so that they will cancel out. 1 foot, 12 inches. And miles, so then I multiply. Feet has to be down here, miles up here. How many feet in a mile? 5,280. So I got miles. But what else do you notice is in the numerator? In the numerator. I got radians right there, right? So if you recall the other day I told you radians is one of those things that sometimes we put the units, sometimes we don't. Sometimes it's one of the very few things where it's acceptable to leave it off because it's not really a unit because a radian is a ratio. So there are times that we leave it where like it is in radians per whatever, and then there's times when you put it in there and the units are there, but they just kind of disappear. You just kind of don't use them, which I know seems odd, but it doesn't happen to really much anything else that we're going to use except radians. So I have it in miles. I need it in hours. I have it in minutes, so minutes has to go up here so that they can cancel out. I can go from minutes to hours. There are 60 minutes in 1 hour. And then that gets my answer in miles per hour. And then figure out what that is. Get 455 pi over 132, and that's miles per hour. What questions do you have? Anything? It's a formula. You put the right things in the formula, you do your dimensional analysis, you're good to go. Okay? There's some basic conversions that you absolutely have to know. Okay? Feet to miles, miles to feet, that's one of them for sure. Okay, we good? Awesome.